Okay, so hopefully now you have a sense for what glaciers are, you have a little bit of an idea for how they work, and now I think it's worthwhile to think a little bit about how they're changing today, how we know they're changing, how we observe them, and what their changes are telling us about the state of the climate and their likely future. To do that, we're going to start by talking about some of the observational methods for understanding glacier change. These two figures here are from a paper that I'm a co-author on that uses ICESat-2 to measure surface elevation change through time. We can see that in some areas the surface elevation is moving down, in other areas the surface elevation is moving up, and it's starting to tell us a complex picture about the interactions between ice and climate. But we'll get into the details there in a moment. Even though ICESat-2 is my favorite satellite, I can't help but admire the GRACE project. GRACE is called the Gravity Recovery and Climate Experiment. It's a satellite that originally launched in 2002, lived to 2017, and then had a follow-on mission, GRACE Follow-On, which is now in orbit. GRACE is a gravimeter experiment. It is an experiment that measures Earth's time-varying gravity field. Because it turns out, by measuring our gravity field through time, we can watch mass redistribute around Earth's surface. The thing that's most active in the Earth system moving mass around is water, because the water system is very vibrant. So GRACE is a wonderful tool for looking at changes in the mass of ice sheets, in water storage and subsurface aquifers, and all these kind of incredibly interesting hydrosphere processes. The way that it works goes back to that law of universal gravitation. So, as we said in an earlier video, the force of gravity is equal to the universal gravitational constant times the product of the two interacting masses over the distance between them squared. The way GRACE works is there are two satellites in orbit. Remember, they're orbiting in response to Earth's gravitational field. They have a shared orbit, but they're separated in space. As the leading satellite comes over the horizon and, for example, starts to feel the mass of the Greenland ice sheet, Greenland pulls on it. That force drives an acceleration, and the leading satellite pulls away from its trailing neighbor. As the trailing satellite starts to feel the Greenland ice sheet, it too accelerates. And so we have this game of cat and mouse. These satellites are moving further apart from each other, closer together, further apart, closer together. And by precisely measuring the distance between them, we can measure the strength of Earth's gravity field in space. As we continue to monitor, we can see how that gravity field changes in time. So, plotted here, I'm just going to start this animation, is a measurement of the change in mass in Greenland and Antarctica from GRACE, measured through time. Red represents mass loss. Blue represents mass gain. You can see in the two time series in the middle that the average mass for both of these systems is negative through time. That's to say, they're both losing mass. In Greenland, what we see from gravimetry is that mass is being lost primarily around the margins of the Greenland ice sheet, where the surface elevation is low. And remember, when you're closer to sea level, air temperatures tend to be warmer. So it's around that warm region along the margins, but you can see it's also concentrated at a few different glaciers or ice streams. There is one in southwest Greenland, Jakobshavn Glacier, where there seems to be a lot of mass loss. Meanwhile, Antarctica's story is a little bit more complicated. We do see that there's a lot of mass loss happening at the western edge of West Antarctica, in the area that we identified as the Amundsen Sea region, Thwaites and Pine Island Glacier. That signal dominates the overall mass change in Antarctica. But we also see some areas around the Saipo Coast that are gaining mass, some areas up in East Antarctica that are gaining mass. And so there are interesting questions. Why might some areas actually gain mass on a warming planet when others are losing? But we see these two patterns. One of our goals is to validate this measurement, because gravity comes with its own uncertainties. So there's this exercise to try and independently measure mass change using multiple methods. The next method we might use is altimetry. So here's ICESat-2, our green light laser, shining light at the surface, watching the surface elevation move through time. And if we can correct for the firn, changes in the firn air content, we can then infer changes in mass from altimetry. So here are two animations that I'll set in motion. The surface elevation change from IceSat 2 in Greenland, the surface elevation change from IceSat 2 in Antarctica. This is over a much shorter time window. IceSat 2 launched in September 2018. This is just the post-launch cumulative change. So for GRACE, we were looking at 15 years. Here we're just looking at 2 years or so. IceSat 2 is much more spatially resolved than GRACE. And we can see similar but more high-resolution patterns. Thwaites and Pine Island Glacier down here, shrinking like crazy, We can see the specific definition of two ice streams that are getting thicker, Cam ice stream and Willans ice stream, whose dynamics are interesting. Why are they thickening? A research question that I'm happy to talk with you more about at a later time. We also see that the outlet glaciers around the margins of Greenland are thinning rapidly. Remember, red is the surface elevation moving down, mass change from that thinning. And that's really concentrated in these fast-flowing ice streams. By contrast, we see large areas where there's either very little or, in fact, a surface elevation increase in East Antarctica. An important thing to keep in mind is that as the planet warms, the tendency is to evaporate more water. That leads to a more active hydrologic cycle. So we might expect that in some areas where the warming that we experience due to CO2 emissions isn't enough to increase the melt of the ice sheets, but is enough to increase the precipitation. And in those areas, we may actually see slight growth through time. We think that's what we're seeing in East Antarctica now. Increased precipitation due to a warmer planet. It's still not warm enough to melt, but it leads to actually a growing region of ice in East Antarctica. So here we've got two independent measures, gravity, altimetry. We also have one final independent measure called the input-output method. The input-output method uses measurements of the velocity of glacier systems, which we can measure using techniques from space, a technique called synthetic aperture radar. We can measure how fast the ice is flowing, and if we know how thick it is, and we know how much snow is being deposited, we can calculate what the difference is between the snowfall and the discharge of ice to the ocean. If that's negative, as in if there's more ice discharging to the ocean than's falling as snow, then we would expect the glacier to shrink. If it's positive, there's more snow falling than is discharging to the ocean, we'd expect the glacier to grow. So there's a group of folks who collect all of these different measures of glacier change and try and create an integrated measure of overall mass change in Antarctica and Greenland through something called the ice sheet mass balance intercomparison exercise. What we see is that these methods largely agree, that gravimetry, altimetry, input-output method all tell a similar story. The West Antarctic ice sheet has a significant negative mass change every year. The DMDT change in mass per year is large and negative. The East Antarctic ice sheet is relatively constant through time, and it's close to zero. Maybe a little above, maybe a little below, still somewhat uncertain. The peninsula has had a relatively flat mass record early on in the IMBY archive, and now has a consistent, statistically significant negative mass change. We can go over here to Greenland, and what we see in Greenland is that as of 2000, it has had significant negative mass balance over its full period. One interesting thing that comes out of this analysis is we can compare the mass changes from Antarctica and Greenland to our projections that have been made from climate models. And what we found from the IPCC AR5, our not most recent, but our second most recent State of the Climate report, they made projections from the early 2000s forward for sea level rise, and the amount of sea level rise we've observed from changes in mass is at the highest end of our projections. It's a little bit distressing, actually. Okay, so what processes are leading to this mass loss? You'll remember that glaciers are defined by the amount of accumulation, the amount of ablation, which can come either from increased calving to the ocean, warming of the atmosphere and melt, enhanced sublimation, or warming of the ocean and melt at marine terminating features, and also ice dynamics. Any one of these three things could change. It could be that the glaciers are speeding up due to some internal process, and they're bringing more ice into the ablation zone, causing them to shrink. It could be that the climate is driving increased ablation, which in turn is changing dynamics and causing glacier acceleration. It could be snowfall is decreasing or snowfall is increasing. We have to tease apart all three of these components. What's happening to accumulation, what's happening to ablation, what's happening to dynamics. Changes in the overall mass of glacier systems that come from the atmosphere, from processes acting on the top of the glacier system, we call that the surface mass balance. And usually when we're studying these glacier systems, we try and tease apart how much of their change is coming from changes in surface mass balance, how much of their change is coming from changes in dynamics. This study from Mougenot 2019 is fascinating. It looks back from 1972 to today and tries to partition the mass changes from each of the different regions of Greenland into its surface mass balance change and its dynamics change. If we just look at the most recent box, anything that's in red is a mass loss. And what we see is for every one of the drainage basins in Greenland, we're losing mass. It's broken down by surface mass balance in the pale color and changes in discharge or changes in the dynamics in the delivery of ice to the ocean in the dark red. And what we see is that Greenland is losing mass kind of 50-50, atmosphere changes, surface mass balance changes, driven primarily by enhanced melt. So enough warming that we're having a longer and more intense ablation season. That controls a little more than 50% of the mass change. And the rest is the glacier's response to that change in melt, the acceleration of glaciers and the delivery of ice to the ocean. About 50-50, leaning a little bit in favor of surface mass balance. Antarctica, by contrast, is still extremely cold. Its surface mass balance is not changing, or at least the melt season is not really changing. It may be the case that precipitation is increasing in parts of Antarctica, leading to a positive surface mass balance. But the net signal of mass loss in Antarctica is driven entirely by dynamics. And to understand why requires thinking a little bit about what's controlling changing dynamics in Antarctica. So as we said before, Greenland and Antarctica are quite different systems. Greenland lives at the northern Atlantic Ocean, where there's large transports of energy northward that keeps it relatively warm. Even though it's in the polar regions, Greenland is on average much warmer than Antarctica. And so melting at the surface is a really important process. We still have iceberg calving, but we don't have extensive ice shelves in Greenland in the way that we have extensive ice shelves in Antarctica. In Antarctica, the process that really controls melt is delivery of ice to the ocean and the ocean heat content available to melt the ice shelves and ice near the grounding lines of these glacier systems. Turns out, surface waters in Antarctica are extremely cold, in part because they're exposed to the atmosphere of the southern hemisphere, in part because they're composed of melted glaciers, or melted ice from glacier systems, or they were just rejected from sea ice formation. The surface waters in Antarctica are very cold. As a reminder, climatically, Antarctica is isolated by the circumantarctic current. Because there's this big ocean separation between Antarctica and South America, we have these strong westerlies that keep Antarctica climatically isolated. So the air temperature there is really cold. The primary source of heat comes from very salty, deep water. We call it circumpolar deep water. Circumpolar deep water. It's about 2 degrees above the freezing point, which gives it a huge amount of heat available to melt. But because it's so salty, it's really dense, and it likes to sit at the bottom of the ocean basin. Oops. For some reason. My eraser stopped working. All right, won't worry about that for now. So to get circumpolar deep water adjacent to the glaciers, which drives melt, you need a process that will pump water up out of the deepest parts of the ocean up onto the continental shelf. It turns out that process, one of the processes that can bring circumpolar deep water up, is applied winds. Winds that are pushing on the surface ocean drive a process called Ekman pumping, which pulls up deep water. So if we strengthen the winds, we strengthen the delivery of circumpolar deep water to the continental shelf, we actively melt away the ice shelves, and then those ice shelves, which are restraining the ice in the interior, they release that back stress, and then ice flows faster. So the connection between anthropogenic warming and melt in Antarctica is very complicated. As we warm the atmosphere, we increase the wind stress in the southern oceans. That increased wind stress drives enhanced pumping of circumpolar deep water onto the continental shelf. That circumpolar deep water melts the ice shelves, and then glaciers flow faster, delivering ice to the ocean. So Thwaites and Pine Island Glacier are delivering ice faster than they ever have before to the ocean, which has put them out of balance. It's resulted in the thinning of ice 100% by these dynamic processes. So we have these interesting patterns. A little bit of growth in East Antarctica due to enhanced precipitation, massive melt in West Antarctica due to the enhancement of circumpolar deep water for these vulnerable glacier systems in the Amundsen Sea, and increased melt season in Greenland that's causing melting along the margins. So that shows you that in order to understand these glacier systems, we need to understand the dynamics of the atmosphere, we need to understand the dynamics of the ocean, and last but not least, we really need to understand how glaciers flow and how they respond to these changes in stress.